Welcome to this lecture. My name is Mark Scythian. The date today is August 9th, 2025. So in this lecture, we're going to prove which system contains the most potential energy. So on the left here, we have a water tower with water isolated in the spherical water tank, a 15-foot diameter spherical water tank, 45 feet above the ground level. So we can start with quantifying the potential energy of the water tower. So we start with the volume of a sphere, 4/3 pi r cubed, and we multiply the constants of 4/3 and pi times half of the diameter, 15 divided by 2 feet cubed. So we calculate 1767.15 cubic feet of water in the water tower tank. And then we know the density of water close to or at sea level is 62.4 pounds per cubic foot. So if we just simply multiply the water density times the cubic feet, as in the water density in pounds per cubic foot, 62.4, we calculate a force weight of 110,270 pounds force. So of course that is a water weight in force, but it would also function with respect to its material, its chemistry, as pounds mass lbm. So we could rewrite that as lbm. So we divide the pounds mass into 2.2, the number of pounds mass per kilogram. So the water tank has a water mass of 50,122.8 kilograms. Next, we calculate the gravitational potential energy, which is mass times gravity times height, mgh. So we know the mass, 50,122.8 kilograms. We convert the height from feet to meters. There's 3.28 feet to a meter, so that's 13.7 meters height. And then we know the gravitational acceleration on Earth is 9.81 meters per second squared, or 32.2 feet per second squared. So we use the metric system here. So the water tower potential energy measured in joules is m times g times h. So we calculate 6,736,353.952 joules, approximated to 6,736,354 joules. So we divide this into a million joules per a megajoule, calculate 6.7 megajoules is the potential energy of the water tower. So we'll convert that to the foot-pounds potential energy at the end of the lecture. So now let's focus on the 5 gallons of gasoline, its potential energy in its non-combusted form. So the energy density of gasoline, or its chemical potential energy, is 20,000 BTUs per pound. And 1 BTU potential is also equal to 1,056 joules of potential energy. I didn't write the 20,000 BTUs in here. I'll correct that in a second. So if we take 5 gallons times 6 pounds per gallon, we know the density of gasoline is 6 pounds per 1 US liquid gallon. So that's 30 pounds times 20,000 BTU per pound. So we calculate 600,000 BTUs times 1056 joules per BTU. And that comes to 633,600,000 joules is the potential energy of 5 gallons of gasoline. So this is 633.6 megajoules. So next we'll focus on the battery. So the formula for calculating DC electrical power in watts is a kinetic energy value, so that's watts. But 1 watt is also equal to 1 joule per second, so that's the kinetic energy measurement in watts or joules per second, but the potential energy is just the joules, not over the function of time, because it's in the potential state. So we can use the watts value and just multiply it times 1 over seconds to cancel out the joules per second into joules. So you just multiply the voltage times the amperes in a DC system, that is. So we have 46,500 watts times 1 over S, so that would just make it from kinetic to potential energy. So we have 46,500 joules divided into 1 million joules per 1 million joules per 1 megajoule. So we get a value of 0.0465 megajoules potential energy in the battery. And that, lastly, we move to the compressed air tank. So we can use the ideal gas law, which is PV, the Pascal's pressure times cubic meters volume, is equal to N, which is the number of moles of the material, in this case air, so 29 grams per mole, times the universal gas law constant, so 8.314 joules per Kelvin mole, and then the temperature in Kelvin. So you can look up the universal gas law constant R. It's 8.314, and then the Kelvin temperature is the absolute temperature in the metric system, so that's Celsius plus 273. But if we actually break down this equation for ideal gas law, the PV side, the left side, represents the potential energy, and the nRT represents the kinetic energy. So that being said, we can just simplify this and solve for PV to calculate the joules potential energy of the compressed air tank. So we can only use ideal gases, so that would be air, nitrogen gas, oxygen gas, hydrogen gas. And so these are examples of ideal gases. But steam, on the other hand, is not an ideal gas, so you could never use the ideal gas law if you're dealing with water in its vapor form, so that's saturated steam enthalpy physics, so you can completely rule that one out. And so now we have the equation we need to calculate the potential energy of a compressed ideal gas. So P is the Pascal's pressure and V is the cubic meters volume. So 1 psi is equal to 6894.76 pascals, and 1 psi is 1 pound force per 1 square inch area, whereas pascals is 1 newton of force over 1 square meter. So if you do the math, you can calculate 6894.76 pascals to 1 psi. So we convert the PSI gauge pressure of the compressed air tank into pascals, and we get 34,473,800 pascals of compressed air pressure. And then we know 1 dry gallon gas is 4.41 liters of volume, but 1 wet gallon liquid is equal to 3.78 liters. So we won't need the wet gallon formulation. We'll only need the dry gallon formulation. So 4.41 liters of air is equal to 1 dry gallon volume. So 1 liter, what is this? This is 1,000 cubic centimeters. So we got the geometry understood with that value. 1 liter is 1,000 cubic centimeters. So 100 dry gallons times 4.41 liters per dry gallon is 441 liters of air. Then we multiply this times 1,000 cc's per liter. So yeah, 441,000 cc's. We find its cube root to get linear centimeters, 76.12 centimeters. Then we divide that by 100 centimeters to a meter, 0.7612 meters. And then we cube that value. We get 0.44 cubic meters. So that is our volume here. So if we multiply P times V, we get 15,168,472 joules of potential energy of the compressed air tank. And we divide that by 1 million, so this becomes 15.17 megajoules is the potential energy. So we'll convert these to the foot-pounds potential energy equivalent. So 1 megajoule is 735,294 foot-pounds. So for the water tower, we have 4,926,470 foot-pounds of potential energy. For the 5 gallons of gasoline, we have 465,882,278 foot-pounds. The battery, 34,191 foot-pounds of potential energy, and then the compressed air tank has 11,154,410 foot-pounds of potential energy. So we have proven the 5 gallons of gasoline has the most potential energy, followed by then the compressed air tank with 5,000 psi gauge pressure and 100 dry gallons of volume, and then followed by the water tower with 1767.14 cubic feet of water, 45 feet above the ground, and then lastly the 15.5 volts DC battery with 3,000 amps of 3,000 amps current potential has the least amount of potential energy. Thank you for watching this lecture and have a great day.